University with collaboration from IUCAA, and recently he has submitted his PhD thesis and got awarded for PhD in physics. Now I will, without taking much of my time, I will request Dr. Jyotirmoy to start his presentation. The topic of his presentation is optical polarimetry.
Thank you very much. Good evening to all of you. In this talk, we will basically this is basically on kinds of discussion. I will share my understanding about optical polarimetry, and let's start. And thank you very much for giving me this opportunity to talk about this optical polarimetry and sharing my idea with all of you. From the very first beginning, from the very first beginning, this night sky germinated the curiosity about this universe to our this humankind. That's why from the this optical this visual domain, basically that's the oldest domain of our astronomy, which basically uh, ignites our ignited our mind. But with the advancement of our science and technology, we have extended our domain of astronomy beyond of our visual range, that is from for gamma ray to radio. Basically, from the ground, what we can observe that there is a very small window, that is a visual window we can observe in this domain, and after that there is a small this near infrared, and after that there is a large window, that is radio. And except that, whatever if we want to observe, then we have to send our instrument above the atmosphere. From the electromagnetic radiation, what we can understand that it has uh, mainly three parameter which we can observe, that is total energy. Then we can find out, we can it has another property, that is wavelength and the polarization. Now, all these parameters has we can have information about the universe from all these three parameters. So to have to measure this total energy, we have one method that is called photometry. To find out the wavelength frequency, we have spectrometer, and there is another one to find out the polarization of the electromagnetic radiation. uh, that for that purpose we do the polarimeter. Now all over the all the modern telescope, the basic back end instrument of all the telescope is, there is, you can get one FOSC, faint object spectrograph. This faint object spectrograph has all these three instrument. This is first is camera for photometry, second one is for spectroscopy, and then polarimetry. And for to get much better high resolution, high sensitivity, then there will be other instruments, individual camera for say high resolution camera with the with adaptive optic system, then spectroscopy for high resolution spectroscopy. There will be one SL based spectrograph which will sit at the Pune focus, then separate polarimeter. Now in this discussion, we'll have a polarimeter. Now before entering in the instrumentation of the polarimeter, we will have the mathematical representation of polarization, and we will slowly enter into the instrumentation of the polarimeter. we can represent any electric field. We can decompose that electric field in the to x direction and y direction. This vectorial, if we do the decomposition of this electric field and x direction, what we will get? This is the amplitude part of that in that x direction. Then there will be varying part, and this is the phase part, or omega t and omega t minus kz. This is the varying phase, and delta x, that is the static. And similarly in the y component. Now the difference between the delta x and delta y, that defines the monochromaticity of the of our radiation. Now, if you do the simple algebra of this x and y component, what we will get? We will get equation which represents on equation of ellipse, where the angle, orientation angle, we will get this two times of the electric field at the x direction, y direction, and divided by the intensity separation. Then cos of delta. This delta is the delta x minus delta y. There's a phase difference. Now chi is the ellipticity angle. I will come to this ellipticity angle later. Basically, this ellipticity is defines the tip of the electric field vector, how it the locus of the tip of the electric field vector is elliptical. Now, the phase difference, this delta, if this phase difference varies from 0 to 2 pi, then the way this ellipticity changes, we can understand from this picture. If the phase difference is at 0, then it will be linear polarized. It will be linear polarized light. If the phase difference is not zero, non-zero, then it will be elliptical polarized light. But the phase delta should, if it is delta less than pi by 2, then it will be elliptically polarized light, and it has one direction. We can see this is the direction of the polarized ellipticity. This is along the along the clockwise. And then if it is delta is pi by 2, then the orientation of the ellipse changes. And on second, if we move further but less than pi, then also orientation is just is going to the reverse direction. But when it's pi, then it becomes on second straight line. This is a linear polarized light. But you can see if it is 0, then it is just there is a angular shift. And from that pi to, if we move towards 2 pi, then we can see the direction of the ellipticity is just reversed, the anti counterclockwise. And from this we say this right handed or left handed polarization. So there is a uh, particular thumb rule for that, and it's a standard the notation. Now we have to represent the polarization. To represent the polarization, there is a one representation that's called Stokes representation. So the elliptical this equation, elliptical equation, if we do the time average to get the measurable quantity in terms of intensity, what we can get one equation. We will end up with equation, this equation. And this equation, if we represent each term as one component, say this E0 x square plus E0 y square, this is as S0. But now we know this E0 x square plus E0 y square is nothing but the total intensity of the electromagnetic radiation. Now the second component E0 x square minus E0 y square we represent as S1, and similarly 2 times of E0 x to E0 y cos delta is S2, and S3 is the I of this 20 ex ey E0 y sin delta. Now, if we write this in terms of Stokes parameter, this S0, S1, S2, S3 are called Stokes parameter, and this is the equation of a sphere, and this sphere we call a Poincare sphere, and we will come to this point, come to this Poincare sphere in the later slide. Here, the notation, if you go for Riviki, then you will get this as IQUV, but in Born and Wolf, it's mentioned S0, S1, S2, S3, and I follow this Born and Wolf notation. Now we'll have a thorough understanding about, we'll inspect each term of the Stokes parameter. What does it mean? Does it represent? S0, that is E0 x square plus E0 y square, already we have identified it as total intensity of the light. Then the S1 term, that is Ex star complex conjugate minus Ey star, that is the difference between the two orthonormal directions intensity. Now what we are considering here, say E0y is 0, then what we will get, S2 and S3 both term is 0, and we will have only S1 term and S0 term. That means this is E0x. There is no y term. There is no component of the electric field along the y direction. So what we can say, that S1 is a completely horizontal polarized light. The polarization direction of the electric field along the x-axis. Now, if we say or E0x, that is the x component is 0, then S1 will be minus E0y. That means this is completely vertical polarized light, and there is no S2, S3 term. So we can have, we can take the total intensity out of this matrix, and we can have 1, 1, 0, 0, that is for horizontal polarized light, and for vertical polarized light 1, minus 1, 0, 0. Now next component is a S2. Now if we have that both components are identical, E0x and E0y both are identical, and the phase difference delta, that is 0. So S1, this S3 term will be 0, and it will be 1, 0, 1, 0. It will be 40 polarized light at the 45 degree, and delta is pi. Then it will be this cos delta is going to be minus 1. This will 1, 0, minus 1, 0. So this is going to be minus polarization at along the minus 45 degree. Now for the S3, the last component of the Stokes parameter, if both component Ex and Ey both are identical and phase difference is delta, then what we will get? We will get S0, S1 term, that is completely 0, then S2 term will be 0, and S3 term we will have only S3 term. So 1, 0, 0, 1. So if we take, if we have this delta is 90 degree and Ex Ey is identical, then this polarization, the tip of the electric field will rotate along the optical, along the locus will be circular, and it will be along the clockwise. And this definition, we call it right circularly polarized light. So we are observer, we are looking at towards the source, and at that time we will see the electric field tip is rotating along the clockwise direction. And if the phase difference is 230 degree, then it will be in opposite. We will call it left circularly polarized light. Now we will come to this point, that what is the degree of polarization. Now light is not generally fully polarized. Light will be partially polarized or unpolarized light. If it is fully polarized light, then we will have that all the points will follow the S0 square plus S1 square plus S2 square plus S3 square, that will form on a equation of a sphere. If it is if it, S0 is greater than this sum of all this S1, S2, S3 square, then it is not going to be fully polarized light. Now what? But S1, S2, S3, these three components are corresponds to fully polarized light. So this is the intensity of the fully polarized part, and A0 is the intensity of the total light. So the ratio of this unpolarized light, but by total intensity, we call it degree of polarization. Now we can any Stokes parameter we can write as a sum of polarized component and unpolarized component. So this part, this S0, S1, 2, 3, all these three components is completely zero. That means this is completely randomly polarized light. This is unpolarized light. And this part is a follows the this point lies on a Poincare sphere, so that's why this is a fully polarized light. Now we'll come to the point, this what is Poincare sphere. Now we understood that S0 square plus S1 square plus A0 square equal to S1 square plus S2 square plus S3 square is a equation of a sphere. So this is a sphere S1, this is a one direction, S2, S3. Now if we have only one point, that is S1, and other points are 0, that means the light is horizontal polarized and it will be on a equator of that sphere. Now if we walk along the equator towards S2, that means we will have no component or along the S1 direction and S3 direction. That means S2 is corresponds to, we understood that it is linear polarized light along the 45 degree. Now once again, if we walk along the same direction and if we come at the negative S1 value, then we will have, this is horizontal polarized light, opposite to that it will be vertical polarized light. If we move once again along the equator at the opposite S2, what we will get? We will get linear polarized light but minus 45 degree. Now if we move towards a pole, what we will get? At the pole we will get only S3 value, there is no other value. So that means it is a completely circular polarized light. But the orientation, direction of the polarization, whether it is right circularly polarized or left circularly polarized, it's just opposite. If it is at the north pole, if it is right circularly polarized, if we represent it, then at the south pole it will be left circularly polarized light. Apart from these, all the points on the upper hemisphere or lower hemisphere, it will be elliptically polarized light, and the direction of the ellipticity from the north to south, it will just reverse. Earlier we came to know that we have familiarized with the ellipticity angle and the orientation angle. So this psi, this orientation angle, you can see the way linearly polarized light, the orientation of linearly polarized light changes with this angle, this psi. That's why it is called orientation angle. And this angle, this is the xi. If we move, if we have larger xi value, then the polarization appears from the linear polarized light to it enters towards the ellipticity. There will be ellipticity, the high ellipticity, and slowly ellipticity goes low, and we get the we get this circularly polarized light. We have now, at this time, we are familiarized with the Stokes representation. Now we will go to the, we will interact with few components of this polarimeter. First component is halfway plate. What is halfway plate? It introduces pi phase in between x and y component. Say this is the electric field E0. It has component E0x, Y component E0y, and this retarder halfway plate, we call it retarder. It introduce pi phase, so it introduce this E0y will be reversed E0y. So what will be the resultant electric field? It will be along this direction, and the angle of this polarization will move. If it is theta degree, then it will be 2 theta. So that means whenever a linear polarized light passes through one halfway plate, and the polarization angle, if it is theta with the halfway plate, then transmitted polarization will be simply, it will be rotated by 2 theta. So that's why it is called rotator. Now if angle is 45 degree and input beam is horizontal, then output beam will be vertical polarized light. Second component is a Wallstone prism. Wallstone prism is made with one birefringent material. Generally, we use calcite material. This is the actual calcite crystal. Out of this crystal, optical workshop produces this Wallstone prism. This Wallstone prism is one very specific component. What it does, if there is any polarized light, then this prism splits the polarization into orthonormal direction. If there is an unpolarized light and we allow to pass through the polarizer, then it passes only that component of polarization which is along the polarization axis of the polarizer. But here it allows to pass both component, and both component are the orthonormal polarized. This is very important component. So this is using this people develop polarimeter. Now how do we measure all the Stokes parameter of the light? There is one very classical method. First, allow the light to pass through a retarder of retardance phi. In halfway plate, it introduces lambda by 2, that is a pi phase difference, but here it introduces phi, arbitrary value. Then allow that light pass through a polarizer whose angle, the polarization angle is at theta degree with respect to this coordinate system. Now the component of the incident beam is E0x, e to the power I delta x, e to the power I omega t, and similarly y. Now when it passes through the retarder, then it introduces retardance at the y direction as well as x direction, and we split it by phi by 2 and minus phi by 2. So this is the transmitted light component after the retarder. Now when it passes through the polarizer, then Ex dash component, there will be one component of Ex dash along this direction. So that is the cos part, and there will be one part corresponds to E dash Y, there will be sine of that part. So this is the total electric field which will be transmitted through polarizer. No other component will transmit from this polarizer. Then what is the total intensity? Then E star. That's all. Now, if you do the little bit algebra, then what we will get? We will get total intensity is equal to half of the S0, that is the total intensity, then S1, first parameter of the Stokes parameter, cos of 2 theta, plus S2 sine of 2 theta. This theta is this polarization axis angle of the polarizer. Then S3 sine 2 theta sine phi. Phi is a retardance of the retarder. Now if we put theta equal to 0, that means this polarizer is horizontal direction, and phi that equal to 0, that means there is no retarder. Then total intensity will be S0 plus S1, half of that. And if we put theta equal to 45, that means we rotated the polarizer along the 45 degree, and without retardance, then we will get S0 plus S2. That means that is third component of the Stokes parameter. Now, if we rotate the polarizer by 90 degree without any retardance, then we will get difference of that S0 minus S1, half of that. And now, if we introduce retardance 90 degree, that means this is quarter wave plate, then we get S0 plus S3. From all these four measurements, we can find out what is the S0, S1, S2, and S3. That means to measure all these four components of the light, we need four individual measurements. For polarimeter, we our main goal is reduce this number of measurement. Now, this is the nutshell of the nutshell of the polarimeter. Polarimeter. So this is a E0 electric field. The component of E0 along x-axis is a E0x, and component of E0 along the y-axis is E0y. Now we know what we know. We know the SO1, that is the first component of the Stokes parameter, that is E0x squared minus E0y squared. That means the intensity of the electric field along x direction of that frame of reference and its orthonormal direction. Now, if you place one polarizer along x-axis direction, then amount of intensity will collect, and if you rotate the polarizer by 90 degree, and whatever intensity will collect, the separation of that will be S1. But here we do another thing. We do the normalization of we find out the normalized Stokes parameter. That's why we divide by the total intensity. Now, to get the second Stokes parameter, what we can do? We can simply rotate the polarizer by 45 degree, measure, this is the polarizer at the 45 degree, measure the intensity, then rotate by another 90 degree, that means 135 degree, measures intensity, and find out this I0 or this difference between both intensity. We will get the third component of the Stokes parameter, that is the linear polarization along the 45 degree. That's all. So that means if we do not use any further components, using only one polarizer, we will be able to measure polarization of the light, the Stokes parameter S1 and S2. But for this, how many measurements we need? We need 4 measurements. From this, we will for the improvement of that, there is a basic polarimeter. This is the imaging polarimeter. It was developed by Professor Ram Prakash in his thesis. What is that? This is on retarder, a halfway plate, and there is one Wallstone prism. Forget this halfway plate. If there is any light is coming incident on this Wallstone prism, then what it will produce? It will produce two image of the source, and each source has polarization at the orthonormal with respect to other image. So this O and E is the O ray and E ray of this Wallstone prism, and the polarization direction is if it is horizontal, then it is going to be vertical direction. That means simultaneously we got two component of the polarization. If we subtract and divide with the total, then what we will get? We will get the first parameter of the Stokes, and after that, if we rotate the Wallstone prism by 45 degree, then we will get the second component. But instead of rotating Western prism, what we do, there is one halfway plate which is in front of Western prism. We rotate by 22.5 degree. That means the polarization, input polarization will be rotated by 45 degree. Instead of rotating Western prism, this is another smart way of rotating the polarization. So at this time, just using two measurement, when retarder halfway plate is at 0 degree, we get S1, and if we rotate by 22.5 degree, then we get S2. So to measure S1 and S2 component, at this time we have two different measurement. So there is one another improvement of this instrument. So that is RoboPol. That is also robotic polarimeter. It is mounted at the Skinagas Observatory, Greece. This is developed by Professor Indra Pukas. Uh, it is four channel uh, polarimeter. The same concept, this Alston prism, but here there are two Alston prism. This is one and this is a second one. Both Alston prisms are mounted basically in the orthonormal. Say this is the crystal axis of the first polar Alston prism, and this is the second one, which are both are orthonormal. And this Alston prism is basically splitting the total amount of light. Half portion of the light is say this one, follow this red line. It produces both component, uh, and there is another Alston prism which produces the another split, and that will be in a horizontal direction because both are normal. Now, one prism, say this is the halfway plate, that is we consider it is at 0 degree, 0 degree, and there is another halfway plate which has angle 67.5, that is nothing but 22.5 degree, and this Alston prism will produce S2 parameter, and this first one 2 3, this vertical that will produce S1 parameter. That means either at a single shot we can measure S1 and S2. This is one of the one of the quickest way of measuring both component of the Stokes parameter. So this is the real time. This is the image. This is on photograph of polarimeter. The size of this instrument will be length will be maybe a feet mounted, and this is the on-sky image of a star. You can see each star is splitted into four parts, and these four spot dots are these four images will be used to calculate the S1 and S2. Uh, that's all. Thank you very much.
Now I will request Arindam sir to take convene this session, and Arindam sir, please.
It is better to if we address the questions that are available at the chat box, and please follow the chat box. There are some questions already arrived.
Right.
Jyotirmoy, please
Huh.
answer the questions.
First question: what is the relationship between the phase angle delta between Ex Ey component of encircle
Electric field, I think.
electric field and the longitude, latitude of the pointer sphere. Okay, so let's come to this point. Here, see, this is the delta. Delta is the uh, phase difference between the electric field in x component of the component x direction and y direction. If we change this delta value, then the orientation angle is this one, azimuth, and the ellipticity angle, uh, altitude, both will change. And and for the value of the electric field components E0x and E0y, we will come to a coordinate, to a point, and at that point it will have different values of the S1, S2, S3, and based on that we will have the different ellipticity of the uh, ellipticity of that light.
The next question is by Arnav Bhadra sir. What physics issue one may address by studying polarization and how?
Right. So, what we can do, we can study the dust property of interstellar medium. We can study the basic the origin of the gamma, these blazars and etc. Uh, Beyond this, at this moment, I do not have much better understanding of that. Is it required the S parameter in a single measurement in the telescope, or use a simple instrument and compute the parameters? It, is it S parameters in a single measurement telescope? Say, see, if we measure the Stokes parameter at different time, that means within that time, if there is any change, we will not be able to understand. We will, if we have measurement of this Stokes parameter at a particular time stamp, then we can get much better clarity. On the other hand, with the time itself, there might be some changes. Some different noise also may introduce in the detector. So that's why, to avoid all this, if we have everything, if we can measure at a particular time stamp, at that particular time stamp, particular frame, then all the circumstance, noise, properties, etc., will be identical for all these components. So that's why it is preferable to have all the components at a measurement of all these components at a single shot.
Okay, Jyotirmoy, I have one question.
Yeah, sure.
Uh, you know, how this, particularly you are talking about dust and all these things. Uh, can you explain the process how this polarization is they are produced, or it may happen that there is polarization and it is fading up? What is happening there?
Sorry.
Two things are there. Suppose there are
Hmm.
lights which are polarized.
Hmm.
They may fade up using dust, and the reverse thing is that some polarization is produced. What is happening in dust? Have you
Okay.
done something about it?
If there is if light incident on any particle, then from that particle itself, it introduce, once light is scattered from any particle, then it will have different polarization. It introduces polarization. So from that, we can uh, we can understand that what is the property of that dust particle, what is and the amount of dust particle is lying within that path also we can understand. In general, whenever light this star emits light, in general it is random, and it is simply
Unpolarized.
coming from exactly this black body radiation. It is unpolarized. So if there is a dust particle in between, then that dust particle will be will introduce uh, polarization. From that we can understand what is the how much what's the mass of that in dust and other properties. But there are some standard stars which has some standard polarization, so that's called standard polarized stars. So this Robopol was basically doing the survey for finding out the standard polarized stars and was doing some laser survey, etc.
Okay, thank you. If
Yeah.
any questions from audience, I think there is no question. Okay, now I will particularly say Arindam Mukherjee sir to unmute himself and give a vote of thanks.
Yeah. Now, polarization, one thing is that there, whether we can determine the source of light, that is the in cosmic source of light, from detecting on Earth's surface through polarization, the, the, the point of origin. Whether polarization can be used as a code, I think.
Exactly.
Yeah.
So from these different mechanisms, say synchrotron and some other radiations from whenever there is a magnetic field interacts with the source, then whenever that source emits light, then there will be polarization at a particular direction. So from that also we can understand the this from we can understand the magnetic field properties, and all the high energy sources has huge amount of magnetic field which can basically alter the alter the polarization direction of the input light. So from that we can study the uh, high energy sources.
Now, if there is no more question, then we give a big hands to Dr. Jyotirmoy Pal for delivering a lecture, illuminating lecture on optical polarimetry. And we also congratulate all the participants here who give an effort to present with us and to hear the lecture of Jyotirmoy. Now, we dedicated this talk to commemorate the 149th birth anniversary of Rutherford, Ernest Rutherford, and who was a physicist as well as a chemist, because he won Nobel Prize on chemistry, and we know his huge contribution. We can remember he's a New-Zealand-born British physicist. All of us know about his famous alpha particle experiment, and he contributed in a lot of fields. The discovery of alpha and beta radioactivity, discovery of atomic nucleus, Rutherford scattering, Rutherford backscattering, and he also with Shoddy, the Rutherford decay model, radioactive decay model. Now, if we have gone through few detail about Rutherford, and we saw that at the very beginning of his childhood, he was not interested in science. He was not from a affluent family. His father was a uh, repair of wheels and maintain repairing and of wheels. And his mother was a teacher. She was a teacher. But from the very beginning of life, there is no his interested was focused on the instruments, that is repairing, mechanic, etc., etc. But once upon one thought that he may be a farmer, a good farmer for harvesting, and rather in the latter field of his study, he slowly he captured interest on science, and especially and more later stage on physics. And he also he in the he did graduations with double gold medal, and he scored very well and took also got for fellowship. But after with fellowship, he also performed very well at graduation. But also after that, he had to suffer unemployment. He didn't get any permanent school job of school teacher. Then he again struggled for another fellowship, and at that time there is a provision that for a particular fellowship, if he can qualify, he can study in any country which was under the ruling of British. And with that facility, he came to Cambridge, University of Cambridge, and did his PhD. And later on, we see that he contributed so much on physics and chemistry. And this is the very colorful life of Rutherford. Anybody interested can study his life from Google. It is there. And with that so much, we we express our heartfelt regard to such a great scientist. With that, we again thank you all and conclude this seminar, I think. And we are very much keen that some more people join this group and some more academic activity can be rolled on with the participation of some academic people. Hence, I request all the academic people who are enthusiastic, who are very interested in the new field of study in cosmic events, please come and join and also contribute by delivering some lecture on some developing topics, some fundamental topics, which can be beneficial for all of us in pursuit of scientific research. Thank you all for this.
Thank you very much. One point I want to mention here, just before conclusion, this image, these are rainbow. Okay. This is rainbow, but whenever you look the rainbow with your sunglass, you may not look at it. So be very careful whenever you look at this rainbow. If you have very good quality sunglass, that will be polarized light, polarizer, that is basically polarized sunglass, and this rainbow has a particular polarization, and this polarization is almost this horizontal direction. This is basically this along the tangent of at each position, whatever you say. So at the top it will be horizontal, and on the other hand, sunglass polarization will be vertical direction, so it will be completely crossed. So at the middle, this portion, you may not see any uh, this rainbow. That's all.
Thank you all.